Hello, my name is Alicia Rodriguez. I work at Syvel, a research center in Spain, and I am here to present the state of the European project Free Drive. This project is titled Free Drives with Low-Cost Manufacturing. Started in October 2017 and lasted 36 months. But due to the pandemic, many of the tasks were stopped and a 6 months extension of the project was requested, so it will end in March 2021. The consortium is made up of 13 partners from 6 different countries, and our total budget is about 6 million euros. The main aim of this project is to further develop rare earth-free traction technologies with a strong focus on industrial feasibility for mass production, targeting lower costs with higher specific torque and power density. The vision is to contribute to a greener European transport by offering new solutions non-dependent on critical sources and making use of the vast electric motor manufacturing capabilities in Europe. In order to reach this goal, several scientific and technological sub-objectives have been defined. First, to design, prototype, and test for high-speed motors, one for each technology, that increase the specific torque by 50% and reduce the motor losses by 50% compared to the project benchmark. To reach a cost reduction in the electric power train of at least 15%, a solution with equal performance characteristics, to develop the power electronics needed for each power setting, increasing the power density by 50% compared to current systems which are being used in the electric vehicles, and to validate the motor technologies by obtaining an integrated powertrain, including all the powertrain systems that will be tested in real driving conditions in the full electric vehicle customized by us. In the project, we are designing, optimizing, and comparing motor designs in 2 rare earth-free motor technologies: copper rotor induction machines and synchronous reluctance machines. In the case of the induction machine, we studied 2 different types of motors for comparison and optimization purposes: fabricated and die-casted copper rotors. And in the case of synchronous reluctance machines, 2 different motors were studied: pure and ferrite permanent magnets. As a result, 4 designs have been obtained for each of the power range settings under study in this project: 75 kilowatts and 200 kilowatts. During this time, optimized design of all these technologies have been carried out, taking into account electromagnetic, mechanical, and thermal performance of the motor under operation conditions. The design met all weight and spacing requirements while complying KPIs, and the efficiency of the machine was evaluated over a complete driving cycle, and it was proved that the maximum performance is reached and the efficiency is about 95% for the designed induction motor. The optimum design for high power level can be scaled and used for various power levels by just changing the power and control unit. This means that the same motor can be used as an electromechanical converter for power levels between 75 and 200 kilowatts. The dimensions will remain the same, and only the power supply levels will change. The synchronous reluctance motor doesn't have an excitation winding in the rotor core. The rotor is potentially less expensive than both permanent magnets and induction motors due to the removal of the cage, winding, and magnets from its structure. But compared to permanent magnet motors, conventional synchronous motors are known for their lower specific power and specific torque, higher noise, and lower power factor. Despite these drawbacks, it's possible to obtain high torque density and high efficiency motors through an optimized motor design. Our final design is as seen in these pictures. And from the 200 kilowatts design, the lower power machine was scaled by only changing the stator winding and stack length. And it was observed that the motor designed fully satisfies the requirements 96%. The main challenge was to design a high torque density motor without the use of rare earth magnets. For this particular project, rare earth-free ferrite magnets were used. The main idea behind using ferrite magnets was to explore new low-cost solutions for high-performance electric motors in order to help eliminating the dependency on rare earth magnets. The final design has been tested at peak power and over the end-user operation cycle and fully satisfied the requirements from performance 96%. In order to further decrease the cost, the 75 kilowatts motors have the same design as the 200 kilowatts machine. Only the active length and the winding are different. To achieve a design that meets these economic requirements, both traction technologies share the same power electronic and the same control algorithms for each use case, medium power range and high power range, and efficiencies of 99% have been achieved with our design. Available solutions have been analyzed and selected for the rest of the powertrain systems needed from an integration point of view, such as battery, gearbox, electric and electronic integration, as well as cooling system and testing systems. The 4 synchronous machines have been successfully tested without major problems. In this blue table, you can see the results obtained, and in the table above, the expected KPIs. The numbers in orange are those that don't meet the KPIs goal. In most cases, the required values have been reached or exceeded, and when they haven't reached, the deviations have been very small. 2 efficiency maps are shown at the bottom of the slide, and it can be seen that the peak system efficiency is about 94%, and the peak motors efficiency is about 96%. We are currently working on the testing of the 4 induction motors and in the testing of the integrated powertrain. We hope to finish this test by the end of this year, and then finally, the motor technologies will be validated by obtaining an integrated powertrain, including all the powertrain systems, batteries, gearbox, etc., that will be tested in real driving conditions in a complete electrical vehicle customized for this purpose. At the same time, we continue with the techno-economic evaluation and exploitation plan of the project. In terms of market introduction, we believe that at the end of the project, TRL 7 will be achieved. And as many processes used in this manufacture, of the motors are mature, market introduction can be carried out in a relatively short time. Based on the success of this project, we have identified some research needs. For example, the span of the power range of the motors, etc. Based on these needs, we are considering applying for new projects in another course. I wouldn't like to end without pointing out that the support of the Commission has been a significant incentive for the realization of this project, and we believe that it has sped up the market introduction of the rare earth-free motors by at least 1 or 2 years. If you want more information about our project, please visit our website or send us an email. And you can follow up in our LinkedIn, where we publish updates to the electric drivetrain innovation cluster. It's all from my side, and thank you very much for your attention.